This title obviously comes from Buzz Lightyear, and he was slightly pompous, I think, or meant to be, and it was meant to be something that was obviously absurd. Well, I'm not so sure that it is absurd, and I hope that by the end of this lecture you might agree as well. Well, the subtitle for this lecture is The Origin and Evolution of the Universe in 60 Minutes, which is fairly tough. But one thing I would say, I have, over the past year or so, given lectures which fill out quite a few of the things that I shall cover, but not in the detail I have in the past. So you can learn more about Einstein with the lecture entitled Proving Einstein Right, more about the expansion of the universe and how Hubble found that out in Hubble's Heritage, about the Big Bang in the violent universe, about dark matter and dark energy in the invisible universe, and all about the cosmic micro background in the title The Afterglow of Creation. So if you can look back at those, you should be able to get some more details. I've got rather more words in the PowerPoint than I normally do. It actually makes a précis of the whole talk. But if you want to, I think the transcript was about 9,000 odd words, and I hope that will give you quite a good feeling of what's going on. Well, let's start. The universe as a whole must be beholden to gravity, because it's the only infinite range force that acts on neutral matter. Electrostatic forces tend to be short range because matter on the large scale is neutral. And of course, the first theory of gravity was Isaac Newton's. And a lot of people say, well, that's obviously wrong. In fact, it only does fail under extreme conditions. And the only case I think it fails in our solar system is to do with the precession of the major axis of the orbit of Mercury, which it doesn't get quite right. That problem was eventually solved by, as you know, Albert Einstein. Way back in 1905, in what perhaps we could call his annus mirabilis, he produced two incredible papers. The first one was about the photoelectric effect, which in some sense is one of the foundations for quantum mechanics, which ironically Einstein did not like at all. And that was what he got his Nobel Prize for, nothing to do with relativity. And then his second paper, and actually it was a supplementary paper as well, was to do with what we call special relativity. And a fundamental part of special relativity is that light travels through space at a constant speed, you all know that. But the important thing is that no material thing, nor any information, however it's carried, can travel through space faster than the speed of light. I've highlighted the word through there, because it does not say you cannot travel faster than light. You can if you're being carried by the expansion of space. This happened very early on in the life of the universe, as we shall see. Think of a currant bun. You take some dough, you put some currants in it, you put it in the oven, gas mark 4 for 20 minutes or something. It comes out, hopefully a bit bigger, so those little currants will be further apart. They have not moved through the dough, they've been carried apart by the expansion of the dough. And that's the idea you have to think of. Well, in 1915, Einstein produced his theory of general relativity, which is essentially a theory of gravity. The theory is pretty complex. It's couched in tensor calculus, and even that wasn't in A-level mathematics when I did it. Almost exactly 50 years ago, I realized as I was coming down on the train this morning. Some nice things to say about it. There's a man that we should know about, but perhaps don't very much, called Chaim Weizmann. He, in fact, he was born in Belarus. He came to the UK. He became a lecturer in chemistry at Manchester University, my own university, in 1904. And in fact, he invented the way of producing chemicals using bacteria, in particularly acetone, and I think that made him very rich. But then he became a statesman, and he was the first president of Israel. So he was really quite a man. I think it was in 1922 he accompanied Einstein on a transatlantic voyage to New York. I should say this is the Aquitania and not the Titanic, which had gone down a bit before, which could well have been the boat that he was on. I did try and research this a little bit. Okay, now, anyway, at the end of that voyage, this is what Chaim Weizmann said. Einstein explained his theory to me every day. I don't need to say it. And on my arrival, I was fully convinced that he understood it. I think that's a lovely quotation. Oh, thanks for laughing. Anyway, now there's another nice story, which I think is true rather than apocryphal. This is the best picture I could find of Einstein with Arthur Eddington. And you may know, certainly if you go back to the Einstein lecture, that Eddington led the expeditions to try and prove that Einstein was right by looking for the deflection of stars close to the sun during a total eclipse. About 1918, a journalist came up to Arthur Eddington, Dr. Eddington, professor he might have been then, and said, "Sir, I believe you're one of only 3 people in the world, apart from Einstein, who understand his theory." And Eddington did not give a reply. After a bit, the journalist said, "Well, that's a perfectly good question, isn't it?" Eddington said, "Well, yes, I'm just trying to think who the other 2 are." So it's not the easiest of theories. Einstein's theory predicts that mass will distort space-time around it, and that gives the surrounding space what we call positive curvature, which means that anything travelling through that space goes in curved lines. To try and explain what it might be, let me try and give you an analogy, which I did give some years ago. You have to imagine a very odd planet, quite big. The lower half is normal, people live there. But everything above the equator is covered with ice, which is a particular sort of ice. It has no friction. The people on that planet are totally convinced that they're living on a flat surface. They're members of the Flat World Society, and they cannot be shaken from that conviction. I know it's silly, you have to accept that. 2 explorers decide they will try and investigate what happens above the equator. They get on 2 sledges 10 kilometers apart, and they basically fire them off simultaneously at the same speed, so they'll travel northwards over the surface of this ice. No friction, remember. Now, they will think that they would remain 10 kilometers apart. That's what would happen on a flat surface. They will be therefore slightly upset when they crash at the North Pole. Now, if they insist on believing that the surface of their planet is flat, the only way they could explain that is to suggest that there was a force that they might call gravity that's actually pulled them together. Do you see that? So gravity is a force that we make up to explain what happens in a curved space if we actually think it's not curved, because we can't appreciate the fact that space is curved. So maybe that helps a little bit. This is rather lovely. John Wheeler, great physicist of the last century. Matter tells space how to curve. Space tells matter how to move. Well, Einstein wanted to solve his equations for the universe that he thought existed at that time, a so-called static universe, unchanging inside. And this was the general consensus among astronomers in the early part of the last century. Now, there's a fundamental problem with this. Supposing there are just 2 things sitting there like that, and everything is just stationary, what will gravity do? It'll make the whole lot collapse down. So he had to invoke a constant called lambda, or sometimes the cosmological constant, which was in effect an anti-gravity term, which has the interesting effect that it's actually stronger the further things are apart, as opposed to gravity, which gets weaker. Now, if you have a force like that, you can see that if you have 2 objects that are just the right distance apart, the anti-gravity lambda force can exactly compensate for the gravity, and the thing remains steady. However, this is a totally unstable system. If they get very fractionally closer together, gravity wins, they'll fall together. If they get slightly further apart, anti-gravity, the lambda term wins, they will fly apart. So it was an unstable universe, and Einstein, when he realized this, called it the greatest blunder of his life. Well, maybe he wasn't quite so wrong as he thought. So it certainly wasn't that particular universe. As you heard, I think, in my last lecture in detail, Edwin Hubble showed that the universe was expanding. Let's quickly look at how he did that. First of all, someone called Vesta Slipher, who doesn't really get the acknowledgement he really deserves, He measured the speeds of approach or recession of galaxies by measuring the blue, if they were coming towards us, or the red, if they were going away, shift in their spectra. You've all heard of the red shift. It turns out that 3 nearby galaxies were coming towards us, but the majority of them, the remainder, were receding from us. So he had measured the speeds of approach or recession of quite a number of galaxies. Now, at that time, there was a real debate about whether the so-called white nebulae, what we now call galaxies, were beyond or within our own Milky Way galaxy. Henrietta Leavitt gave the clue as to how to solve this problem. She had observed a type of very bright star, they're called Cepheid variables, after the star Delta Cepheus, discovered by John Goodricke, an Englishman. These stars increase in brightness quickly, fall away more gently. Increase, fall away. So it's a very rhythmic oscillation of the star, going in and out. These are very, very bright stars, some of the brightest stars we have, which means you can see them at great distances. That's good. She observed a whole range of them in what is called the Small Magellanic Cloud, which is down here. We're here. So they were all at about the same distance. And she discovered that, in fact, the brighter ones were breathing more slowly, which is not really surprising. A bigger object is likely to be brighter. If you took a big bell and a little bell, the big bell would actually have a lower tone than the little bell. So the bigger stars are oscillating a little bit more slowly than the smaller stars. And those that oscillate with a period of about 30 days are typically about 10,000 times brighter than our sun. And obviously there's a range, but that's a particularly useful one, 30 days. The first major discovery that Edwin Hubble made was by observing our nearest giant galaxy, the Andromeda galaxy. He observed what he first thought was an N-type star here, but then realized it was a variable star. It was a Cepheid variable. This was in the 6th of October 1923. And from that, he was able to compute the distance of Andromeda and showed it was way outside our own Milky Way galaxy. The universe became vastly bigger, effectively, on that day. Well, he then measured the distances, using that technique, of all the galaxies that had been observed by Vesto Slipher. And he made a plot. Here is the distance. This is a very big distance, and that's quite as big, twice as big a big distance along that way. That's a megaparsec, which is 1 million parsecs, which is 3.26 million light years. It's a long way. Now, he noticed that galaxies at about 1 megaparsec distance were going away from us at about 500 kilometers per second, whilst those that were at 2 megaparsecs were going away at 1,000 kilometers per second. Now, you might say that's a bit of a guess, really, that that's a straight line, but he then, a bit later on, 1931, with his assistant Humason, they extended the Hubble plot to a much greater distance, and I think we would agree that that's not a bad straight line. That tells us something totally significant. It tells us that our universe is expanding. And I've made this very simple universe, perhaps to try and explain that. We've just got 3 objects, red, green and blue. They're each 10 miles apart. We will let that, quote, universe expand by a factor of 2 in just 1 hour. So at the end of that hour, can you see we've got a distance of 20 miles and 20 miles. Everything's twice as big. If you look at the green one from the red one, in that hour it has gone 10 miles. So its average speed of recession is 10 miles an hour. If you look at the blue one from the red one, in that hour it will have gone 20 miles. Average speed of recession, 20 miles per hour. And if I extend this to many, many more, you'd find that the more distant ones appear to be going away from us at a speed that is proportional to their distance. And that's exactly what Hubble had observed in the galaxies, and that told him, and tells us, that our universe is expanding. That's exactly what I've said there. And I just want to say something about the redshift of these distant galaxies. they're being carried away from us by the expansion of space. They're not moving through space. But when we look at a very distant galaxy, we're seeing it at some time in the past. Could be a very long time in the past. And if we have an expanding universe, at that time, the universe would have been smaller. As since then, the universe has expanded, so the wavelengths of the light being carried through it expand by the same ratio, so they become reddened. And this is what we call the cosmological redshift. So from this, Hubble produced what we call Hubble's law. The velocity of recession, due to the expansion of space, I've written there, is proportional to the distance and related by Hubble's law, which is in fact the velocity is equal to a constant, which is Hubble's constant, times r. We put the 0 there because it's actually the value of Hubble's constant now. Over time, if the rate of expansion, as we will see, has changed, then in fact Hubble's constant isn't really a constant. It's something that's actually changing with time. But h0 is the current value. And remember I talked about a galaxy 1 megaparsec away, travelling at about 500 kilometers per second. So the value of h0 that Hubble got was 500 kilometers per second per megaparsec. Okay, so now a bit more cosmology. We know now that the universe is expanding. In fact, prior to that knowledge, Alexander, and I have spelt that correctly, I think, Friedman, solved Einstein's equations to produce an infinite set of models of expanding universes. Now, I've tried, at least in the PowerPoint, to use a small u when it's universes in general and a big U when it's our universe. I hope I've been consistent. They're called the Big Bang models because they all start with what is termed a singularity. And it is said that that was a derogatory term given them by Fred Hoyle, who opposed them, as we shall see shortly. In fact, I think in his later life he said it wasn't really that, it was just a name he made up, and it's a good name. By the way, there's a lovely book about Fred Hoyle, just published by Cambridge University Press, written by Simon Mitten. Has anyone seen it? I was lucky I got a copy to review, so it doesn't cost anything. Anyway, it's a good book, and I thoroughly recommend it to you. It's a very, very good book. Now, in the Friedman models, the universes all begin in a point singularity. And those that came to my lecture about the Big Bang know that I do not like singularities. I say it is simply when the laws of physics of that particular theory breaks down, which is certainly true in Einstein's theory. In fact, I would say that that means the standard Big Bang models could not in fact be correct, which we shall find out is the case. But for the moment, just imagine that all the matter of the universe was concentrated at a very, very small point. The initial high rate of expansion falls with time due to the mutual gravitation of all the matter in the universe. Just in the same way, if I take a ball, I throw it up into the air, the velocity, speed going upwards, slows with time. That's just the gravity of the Earth acting upon it. And these are the models. It depends upon how much matter is in the universe, the density of matter, as to what happens. If there is enough matter in the universe will expand to a maximum size and then collapse down to a point that we call the Big Crunch. And of course there are an infinity of models in here. Like that, like that, like that, like that, and so on. So that's an infinity of what are called closed universes. They are ones which will eventually come back to a Big Crunch. On the other side, we have an infinite number of open universes where, in fact, the expansion carries on obviously faster and it will never fall back to a Big Crunch. But there is one individual case between all of these and all of those, which is called the critical universe, sometimes called the flat universe, as we shall see, where it's just like the escape velocity of the Earth. Given nothing else in space, a rocket leaving the Earth with escape velocity would leave the Earth, it would go slower and slower and slower and slower, but never actually stop until it gets to infinite distance. So that's the so-called critical universe. It will expand forever at an ever slower rate. The critical, or as we shall see, flat universe, is the boundary between all the open universes and all the closed universes. The universe is then said to have a critical density. If the density is greater, that means there's more mass, we get the closed universes, ending up with a big crunch. The ratio of the actual density, that's what the universe really is, to the critical density, is a factor. It's called omega. If omega is greater than 1, i.e. we're denser than critical, we have closed universes. And in fact, in those universes, space on the large scale is positively curved. Come back to that in a minute. If omega equals 1, we have the critical universe, and they say, and I don't like it, that space is flat, which almost implies it's two-dimensional. It doesn't. What it means is that in such space, Euclidean geometry holds sway. If you have any triangle in any orientation in this Euclidean universe, the angles inside will add up to 180 degrees, and two laser beams starting off parallel will remain parallel forever. And finally, if omega is less than 1, we have open universes, and in these space is negatively curved. And I will use this idea later on to try and show you why we believe, in fact, that space on the large scale is flat. And that's just a two-dimensional analogy. There's our flat universe, omega's 1, triangles 180 degrees. On a positively curved universe, omega greater than 1, these angles add up to more than 180. And on a negatively curved space, like on a saddle, the angles add up to less than 180. But we'll come back to that later on. I do want to make that point now, though. Now, this is quite interesting. If you assume a constant rate of expansion, which is not true in any of those models, but supposing you do, then you can extrapolate backwards in time until the universe had no size, its origin. And that time, or that age, is called the Hubble age or the Hubble time. Both of those terms are used. And you get it simply by going 1 over the Hubble constant. It's very simple. Well, it takes a page to do it, but don't worry about it. All you need to know is it's 2 billion years. If you take Hubble's value, 500 kilometers per second megaparsec, expand out, it comes to 2 billion years. Now, in fact, that is this. This is now, that's the value of Hubble's constant now, h0. You backtrack in time and you get 1 over h0, which is that time. Now, if you think about those Friedman models I've just shown you, all of those began with a greater rate of expansion. This is, in fact, the critical one. So can you see that the Hubble age is bound to be bigger than the real age? Is that obvious? Somebody say yes? Yes? Okay. So, in fact, if it is the critical or flat universe, it turns out that, in fact, the actual age is 2/3 of the Hubble age, which is about 1.3 billion years. And so that was the value they got, basically around 1929. Now, that may worry you. I hope it will worry you, because we know that our Earth, and people are beginning to know the age of the Earth, about 4.5 billion years, and calculations significantly made by Fred Hoyle and others on the evolution of stars, for which he jolly well ought to have got the Nobel Prize, basically showed that at least some stars had to be really greater than at least 8,000 million years, 8 billion years. So essentially, the universe, things in the universe, cannot be older than the universe itself. So obviously there was something wrong, and theoreticians, plenty of them, said, well, could the Big Bang theories be wrong? And as many of you will know, in 1949, Fred Hoyle, Thomas Gold and Hermann Bondi produced a rival theory of cosmology called the steady state theory, or the theory of continuous creation. Now, in this theory, they extended what is called the cosmological principle. So all cosmologies adhere to the cosmological principle, which is what one would see on the large scale at a specific time will be the same everywhere in the universe. So no matter where you are in the universe, if you all look at the same time relative to the origin, it will look the same. And that actually has been very nicely proven by the Hubble Space Telescope. It's made the Hubble Ultra Deep Field North in Ursa Major, which is this picture here, the Hubble Ultra Deep Field South, somewhere in the southern hemisphere, almost opposite in direction, and essentially the universe in those very distant locations, well away from each other, look the same. They extended that theory to basically produce what they called the perfect cosmological principle. And all I've done is to add 3 more words. It's the same everywhere in the universe for all time. The universe would be unchanging on the large scale. Now, they knew that the universe was expanding, so that would mean that the galaxies would gradually be moving further and further apart from each other. But their nice idea was that in the space between the galaxies, new matter, in the form of hydrogen, was being created. And rather nicely, you could never possibly detect that rate of creation, so it's good when you can't test theories, but we'll see there was another way. Anyway, that hydrogen would eventually form galaxies, so the average density of the universe would remain constant, even though the universe was expanding. The rate of creation of new matter, as I've said, is too low to observe. There is a bit of a problem, though. They said that you'd only make hydrogen, and there's quite a bit of helium in the universe, about 25%, increasing now, actually. And essentially, they thought that happened in stars and in explosions, and really it doesn't look as though you could actually make the amount of helium that we see. But the really important thing was that the theory was, in fact, testable. And it's actually a very easy thing to do. This is the universe. This is our Milky Way galaxy. This is the space nearby. And I can take a volume of space, 100 cubic megaparsecs or some big number, which contains lots of galaxies, and I can measure the density. Fair enough? I know how many galaxies there are per cubic megaparsec. I can now look right back to the origin, or near the origin of the universe, perhaps 8,000 million years. And I can take the same volume of space, and I can measure the density of the galaxies in that. If it is steady state, the number I measure nearby will be exactly the same as the number I measure far away, far back in time, because the universe is unchanging. However, if we have the Big Bang models, the universe getting bigger with time, then in fact I'll find more galaxies per cubic megaparsec here than I will find there. Does that, hopefully that's fairly logical. So that's a testable thing. And in fact, Martin Ryle, previous Astronomer Royal at Cambridge, set out to do this by observing radio sources. Now, in those days, the early 60s, we could actually see more distant objects, I think, in the radio part of the spectrum than they could in the optical. Things have changed now, we're equally good, but in those days, radio was somewhat better. So he built an array of antennas at Cambridge to try and do this. In fact, that's Martin Ryle. This is Francis Graham Smith, who was the director of Jodrell Bank for many years. I make most of his PowerPoint presentations for him, actually. It's one of my roles in life these days. Anyway, it happened that Ryle's results, the first set, showed a great excess of distant sources over nearby ones. Steady state was rubbish. Now, look, if you read this book about Hoyle, you find that he and Ryle didn't get on too well even before this happened. Now, the trouble was, Ryle said, steady state, useless. But then the people actually in Australia said, Ryle, most of your radio sources aren't real, and therefore your results aren't any good. And you can imagine what Hoyle felt when he heard that. And there was seriously worse in pretty enormous rows. I'm not sure it's quite subtle, this. I'll try and explain it, what went wrong with the Ryle results. Could you imagine 3 stones dropped into a pond simultaneously? Can you imagine there's a bit of water splashing about where they are? Imagine those are radio sources. But those impacts would cause ripples, wouldn't they, to run out across the pond. And there will be places where the ripples from all three, or even more, can you see they sometimes add up, sometimes don't? And there'll be some places where there was a little bit of a bump of water just due to the combination of the ripples from the real three stones. Do you see that? Well, it's not exactly that, but that's the same sort of idea, that the way they were doing things, a point source would have a pattern of ripples around it, and occasionally these could add up to make you think there was a source where there wasn't one. We call it confusion. That was the word. That's the word. Well, they had another go and another go, and finally, on the third go, they got it right. But can you imagine Hoyle didn't believe a word of it? The data still showed that radio sources were more closely packed in the early universe. Hoyle was not convinced. Not long after, though, there was a final knockout blow to the steady-state theory, but even that, in fact, Hoyle didn't really agree with. But let me explain what it was. We need to go back in time a little bit to a rather wonderful physicist called George Gamow, and I was lucky enough as a first-year postgraduate to be taught by him for a short while. And he was the first to point out that if the universe had been very hot at the beginning, in the Big Bang, then there should still be some radiation left over that would pervade the whole of the universe. And the point was this: if you put a thermometer in the middle of nowhere in the universe, as far away from anything you could get, it would not say absolute zero. It would have a temperature, because as the universe gets bigger, that temperature will reduce but will not go to zero until infinite time. And in fact, it wasn't him, but his two students worked out it might be about 10 Kelvin. We call the radiation left over from the Big Bang the cosmic microwave radiation. It turns out that in the first 380,000 years of the life of our universe, it was too hot for atoms to form. Because if you had a proton and an electron, a photon comes along, kicks the electron off, and so it's what's called a plasma. You have free electrons. The matter and the radiation were interacting, which means they actually have the same effective temperature. And also, because the light and radio waves, for that matter, are being scattered off the electrons, it is just like light being scattered off water droplets in a fog or in a cloud. The universe was opaque. Finally, about 380,000 years after the origin, it was cool enough for atoms to form. And at that point, no free electrons, the universe became transparent, and so that's as far back in time as we can see. We know at that time the temperature of the universe would have been about 3,000 Kelvin. We also know it would have had what's called a black body spectrum. It's the same like the spectrum of the sun, which is because the light and the matter were in thermal equilibrium. Since then, the universe has expanded by about 1,000 times. As a result, the temperature should fall, in fact, by just the same ratio. It should be about 3 Kelvin. And that's the idea, I've mentioned it earlier, that as the universe expands, so the radiation wavelength, when it expands by just the same ratio. This was the black body radiation, 400,000, just under years after the origin. Peaking in the yellow part of the spectrum. The universe would have looked like sort of a yellow-orange, 3,000 Kelvin. This is what you'd have now. It doesn't peak in the visible, it peaks in the far infrared and the radio, which is good for radio astronomers because it means that to study the very early universe, you can't be an optical astronomer, you've got to be a radio astronomer. Excellent. Okay, as we'll see. So the CMB now peaks in the far infrared and the very short radio wave part of the spectrum. And we now have one of these rather lovely serendipitous discoveries. I know I've mentioned it before, but many of you here might not have been to that lecture. But very briefly, it's this. The telescope you see in the back there at Holmdel in New Jersey, owned by Bell Telephone Labs, was actually used in some of the first satellite radio transmissions, television transmissions. When it was completed its use for that, it was given to two astronomers, two radio astronomers, Penzias and Wilson. Penzias had built a superb receiver, and they put it on the back of the horn, inside the little lab at the left there, and started to test it out. And they got a bit unhappy, because it was producing more noise than it should have done. If you put the sound coming out onto a loudspeaker, it just sounds like white noise, a hissing sound. That sound was just a bit too strong. It wasn't the receiver, they tested that separately. It didn't matter where they looked, it was the same. That implied it had to be something in the horn antenna. Well, there was something. Just close to here, where it was warmest, a pair of pigeons were roosting. And pigeons are warm-blooded animals, so they have a temperature, room temperature effectively, or outside temperature. They radiate radio waves. So they're very good. They bought a have-a-heart pigeon trap. And look, I kid you not, this I picked up off the web 2 days ago, have-a-heart. Here we are, you've got a feral cat. This is a raccoon trap. They're all much the same. I did not find pigeons down there, actually, but I assume they do. So that was a have-a-heart trap. That trap, by the way, is now in the Air and Space Museum in Washington. Over 2 days, it is said, they captured the 2 pigeons. What to do with them? Well, Bell Telephone Labs had a laboratory 40 miles away, a place called Whippany. They put them on a little truck that was going there for a daily little trip and arranged for one of the technicians to release them, which they did, and of course they flew straight back. So they shot them. So they were shot. So that was all right, except that while they'd been in there, they had left the interior of the horn covered with what they said actually in their paper in Science was a white dielectric substance, guano or something. They got rid of that. It didn't really make any odds, frankly. Well, Wilson was travelling on a plane from Boston to New York, or maybe New Jersey, to be honest. On that plane, by chance, he met someone that my colleague here and I know quite well called Bernie Burke. He was a research fellow at Jodrell Bank for some years. And he asked Bernie Burke asked him, you know, what's the problem? Have you got any problems? And he said, yes, we've got this noise we don't understand. Bernie Burke knew that at Princeton, someone called Richard Dickey was building, or his students were building, a horn antenna on the roof of the physics department because Richard Dickey had also realized that the universe would be full of radiation and that you could detect it using radio technology. So that's what he was trying to do. Bernie Burke told Wilson, when you get back, ring up Richard Dickey. They rang him up while Richard's group were having tea. And Dickey put the phone down and said, we've been scooped. And the next day they went across to Holmdel and said, yes, you have discovered the cosmic microwave background, for which, of course, they got the Nobel Prize. I feel it's slightly sad that Richard Dickey didn't either, but that's the way it goes sometimes. Now, to be honest, that was a measurement at one frequency. To be totally sure it really had come from the Big Bang, you really had to have that black body spectrum. And it wasn't actually until 1992 that a spacecraft called COBE, with a thing called FIRAS, the Far Infrared Absolute Spectrophotometer, was able to show that the power spectrum of the radiation left behind was perfect. The error bars fit within the theoretical line. And I think it's fair to say that since that date, no one has disputed the fact that there was a hot Big Bang. I think that's absolutely solid. So, to summarise that, Penzias and Wilson discovered the CMB in 1965. It was shown to have a black body curve, and there was a Big Bang. We had Hubble's constant. That started all the steady-state theory off. Well, basically, it turns out there are 2 types of Cepheid variables, and the ones that Hubble was observing in Andromeda were in fact brighter than the ones that Henrietta Leavitt had observed. So all the numbers were wrong. Gradually, over time, that value of Hubble's constant has improved. We now believe it's about 74 kilometers per second per megaparsec. Very quickly, there used to be 2 groups. One group reckoned it was 100, another group reckoned it was 50, and they would shout at each other at conferences. And then at Jodrell Bank, using something called a double quasar, and 1 or 2 others, we came up with a completely independent way of calculating it and got about 68. It's been wonderful to see since that time, many years ago, how the hundreds have come down to 70 and the 50s have come up to about 65. And that is because they now know what the right answer was. But even if you take a value of Hubble's constant of 74, which is about plus or minus a teeny bit, the age in the Friedman models is still only 10 billion years. And I think more modern computations of stellar evolution suspect that some stars are distinctly older than that. So I still think that this is another reason why the standard Big Bang models cannot be correct. The universe in them is not old enough. So, problems with the standard Big Bang theories. The first one is that as far as one could measure, and I'll actually show you how it's done a bit later, the curvature of space in our universe is essentially very close to zero, i.e. flat space. Now, remember, that was just one possibility in an infinite number of solutions. Why should it be that close by chance? In fact, that value of omega, which is 1 in that case, would have had to have been in the range of that to that 1 second after the origin of the universe for it to be close to 1 now, because any deviation from 1 actually gets bigger as the universe ages. That is incredibly fine-tuning. There's nothing in the standard Big Bang models to explain why that should be so. The second is called the horizon problem. Now, we're here, and that CMB, the Holmdel telescope, looked essentially 14, nearly, 1,000 million years back in time in that direction. That radiation is just reaching us. And it measured a temperature, 2.753, I think. You look in that direction. That radiation is just reaching us. You see exactly the same temperature. But the point is that no radiation from there has had time to reach over there. Do you see that? The universe isn't old enough. So how on earth does that bit of the universe know the precise temperature of that bit? Do you see there's a problem there? I want to give you an analogy. I'm on a British ship, and that's, I think, the red ensign, all right? Now, over the horizon, I see another ship. It's black, so it's obviously not a nice ship. It's got some sails, and it has a flag. So I can't actually see the base of it, to be honest. I'm really just looking at the top part, but I see it there over the horizon. And because I'm an astronomer, I go up the mast with my telescope, and I look out at the ship, and I can actually see I've blown the flag up. So it's got a flag, a Pacific flag. Now, while I'm up there, I happen to look in the opposite direction, and I see another ship. And I see it's got exactly the same flag. Now, would you agree, because of the curvature of the Earth, the people in that ship over there could not see that ship over there? Fair enough? So how have they got the same flag? At some time in the past, they must have been close enough to each other, perhaps in the same harbour, so that someone could give them the same flag to fly. The theoretical term is they have had to have been, in the past, in what's called causal contact, within a volume of space so that light could travel, information could travel no faster than the speed of light to join them, in effect, together. So they've got the same basic information. Can't travel faster than the speed of light. Now, how on earth, therefore, can that part of space know what that part of space is like? Well, the idea was produced by a scientist called Alan Guth, for another problem I won't go into to do with magnetic monopoles. I was awfully chuffed when I found this picture on the web, and I've included it because my wife is in the audience, and I wanted to convince her that some people are probably somewhat more untidy than I am. But there is Alan Guth. Now, his idea is this. It's called inflation. At some time in the past, somewhere way back, a little bit of space suddenly blew up. It may have started as a quantum fluctuation out of effectively nothing. But it blew up by a factor of around 10 to the power 60, somewhere between 50 and 60. So eventually ended up as something about the size of a metre across. It's called inflation. And you don't get much better inflation than that. And things, by the way, during that inflationary period were moving apart distinctly faster than the speed of light because it was the space expanding. Now, that actually generated a vast amount of energy. And we'll see what happens to that energy in a minute. But the important thing is this: if you took a balloon and blew it up by 10 to the power 60 times, would not the surface look flat? So if you blow up our universe by that sort of amount, what might have been initially positively curved becomes essentially flat. So that forces the space in our universe to be flat. But the other point is this, that prior to the inflation, everything that there was close enough to be in thermal equilibrium. So after it, even though things have travelled faster than light, things could all be at the same essential temperature. We had a homogeneous universe, which is why we see it now. So inflation solves the flatness problem and also solves the horizon problem, because all of the universe was in what's called causal contact before the inflationary period. I talked quite a bit about the Big Bang in that lecture called The Violent Universe, but very simply, during that inflationary period, a vast amount of energy, in some sense, was created. Half of it was gravitational potential energy, which we'll call negative, and the other half was positive. And it's a bit like having a car on the top of a hill. It has what's called potential energy. If you push it down the hill, it loses potential energy and gains kinetic energy. The two are sort of equal and opposite. One's positive, one's negative. And in fact, the net energy would be zero. So there was nothing, the totality of everything in the universe, if you could make it all fall back down together again, the energy released by all the potential energy would exactly equal the energy that makes up all the matter. So our universe is just a big sort of aberration from nothing. And in fact, that only happens in the case of a flat universe. So that's another reason why the universe has to be pretty flat. Out of that sort of positive energy were created particles, an almost equal number, we believe, of matter and antimatter particles. But by some little asymmetry, there was perhaps 1 part in 8 billion, an excess of matter over antimatter. All the matter and the antimatter annihilated each other, and that gave rise to all the photons that make up this cosmic microwave background. The normal matter particles that were left over were mostly up and down quarks and electrons. The quarks combined in groups of 3 to form an almost equal number of protons and neutrons. But the neutrons by themselves are unstable, with a half-life of about 16 minutes. So many of those neutrons turned into protons. So the number of protons went up, number of neutrons went down. The only neutrons that remained were those that were effectively captured to form helium nuclei. And those were essentially the two major elements. 75% hydrogen, 25% helium that were created in the Big Bang. As I've said, it was so hot then, the atoms couldn't form. Only after about 380,000 years did the universe cool sufficiently to allow the atoms to exist. Okay, inflation predicts, and observations, which I'll show you shortly, seem to require that space is flat. If that is the case, it's an easy calculation to work out the average density of matter in the universe. It's about 1 hydrogen atom per cubic meter, something like that. It turns out that the normal matter that we can see, stars, etc., ionized gas, as well as things we can't see, normal gas, dust, black holes, whatever, only makes up about 4% of the total mass energy content of the universe. And as I talked about in that Invisible Universe lecture, dark matter can help solve this problem. And we have a vast amount of evidence now that dark matter must exist. One of them is this. In the terms of planets going around the Sun, the outer planets move more slowly. That's called Keplerian motion. And it was thought that the outer stars of a galaxy, well out from the matter, concentrated at the centre of a galaxy, would be going round more slowly than the inner stars. It turns out that's not the case. If anything, the stars near the edge of a galaxy are going round slightly faster, certainly at the same sort of speed. The only real way you can explain that is that the galaxy is embedded in a halo of what's called dark matter, whose gravitation effects obviously affect the motion of the stars. And a great guy, not well liked by his colleagues, called Fritz Zwicky, he observed a lovely cluster of galaxies called the Coma cluster. Now, if you think about it, if you had maybe 1,000 galaxies all sitting there doing nothing, gravity will make them collapse down. On the other hand, if you made all those galaxies go very, very fast indeed, they just fly apart. The fact that that Coma cluster still exists, perhaps 8,000 million years after it was formed, tells you something. It tells you that the gravity that's trying to prevent them escaping is roughly comparable to the energy of their motion. It's called the virial theorem. From that, if you measure the energy, the motion of all the galaxies, you can work out the mass of the cluster. And it's several times more than what you can see. So we believe that this is, in fact, the result of dark matter. We don't know what it is yet. There are lots of experiments going on to try and find it. Things called neutralinos are quite likely. A WIMP is a weakly interacting massive particle. That makes it very hard to detect. As I said, searches are actively taking place, including at the bottom of the Bulby mine in North Yorkshire, where they have a lot of experiments. So I can't tell you what it is, and I've shown you this before, but I can show you precisely what it looks like. But we still have a problem. Of all the mass energy required to make space flat, we now think we've got 4% normal matter, 23% dark matter, which is 27%, if I can add up. That leaves you 73%. What can that be? Well, we say it might be dark energy, an energy of the vacuum of space. We have some evidence for it, it turns out. We can observe very bright objects called Type 1a supernovae. When they explode, they're probably brighter than the whole of the galaxy that they're embedded in. They're the result, in fact, of a white dwarf being overloaded with mass, so it actually collapses and undergoes a thermonuclear explosion. And because the way this happens, we suspect that all have the same peak brightness. It makes them very good standard candles, because if we see one 1,000 times fainter, no, let's say 10,000 times fainter than a nearby one, same brightness, the far object would be 100 times further away. So it's a way of measuring the distances to very, very distant galaxies. For example, there's a supernova in this little faint galaxy here, as seen by the Hubble Space Telescope. And here a whole set. The Hubble's done a wonderful job on this, and I did mention this when I talked about the Hubble's heritage. Here, this is before, and this is after, and someone's kindly put arrows on the sky to show us where the supernovae are. You can see them here. So we can now extend that Hubble plot out to vastly greater distances, and there it is. The Supernova Cosmology Project has been doing that work. And it's always been known, because we do not expect the expansion of our universe to have been linear over all time, and the Friedman models, it would have been expanding more quickly in the past, that plot would stop being linear when you go far enough back into time. And it does. These are not on that straight line. And I can make it more obvious by making that diagonal line horizontal. So I've just basically flipped that line here and made that go horizontal. And here it fits pretty well. Down here, it's way away. But there's a fundamental problem. In all those Friedman models, the values should have been down here. They should have been below the line, not above. And that tells us that now the rate of expansion of the universe is not decreasing with time, as in those Friedman models, but increasing with time. The rate of expansion is increasing. We live in an accelerating universe in some sense. Now, that could well be, and at the moment all the evidence suggests that it is, this cosmological constant term, the lambda term in Einstein's equations that he thought was his greatest blunder. That could do exactly what is currently observed. So, what do we actually know now? Let's just come right up, in fact, to about a month or two ago. The density fluctuations, the universe wasn't totally smooth when it first became transparent. We can look back and see tiny fluctuations, 100 or so microkelvin in the brightness. The first really good observations were done with the Boomerang spacecraft. And basically they let it off at McMurdo Sound, the American base in Antarctica, and the winds take it all the way around in a circle and bring it back 10 days later. Do you know, I've always had this worry about these people that sail around the world, because really they go straight south, whip round Antarctica the right way and come back up again. I sort of feel you should go through the Suez and Panama canals, but anyway, that's a minor point. But basically the winds will take you around Antarctica. I'm not betrying what they do, I just find it amusing. Anyway, this is a map of those cosmic microwave fluctuations, and you can see there's quite a lot of structure on a sort of a scale size this much, which is about 0.8 of a degree. Now it turns out one can compute precisely what the sort of pattern should be. And let me try and give you an example to show you what we think, how this tells us what space is like. Imagine that at the back of the room there was one of these patterned wallpapers you get in the Indian restaurants, you know, a repeating pattern. Okay? The space between it and me, we'll assume is flat, light travels in straight lines. I see precisely the angular scale of that pattern, as was. Would you agree? Is exactly what it looks like. Supposing, however, the space is positively curved, and I've got here, coming out of an achromatic telescope, I hope I can put it back together again, here is a very nice convex lens. If I hold that up, in fact, I can actually see that things at the back of the room seem further apart. Can you see the scale has expanded? Because that's a convex lens. That's what happens with positively curved space. If I, on the other hand, put up a negative lens, a concave lens, well, you all look smaller and further away. Everything looks smaller. So, if we measure the scale of the fluctuations in this cosmic microwave background, we can tell whether it's what we expect, smaller or greater, which tells us what the curvature is. And this is a simulation that was done. Those are the Boomerang observations. That's what you'd expect with positively curved space. This is what you expect with flat, that with negative. And it looks pretty close. And you'll see that's been even better in a minute or two. This is a wonderful spacecraft called WMAP. That has produced an all-sky map of these fluctuations. And that's been analysed in great detail. And it gives you a plot. Now, don't worry about this, but basically, this is the peak of the fluctuations. It's at 0.8 of degrees. That's exactly what you'd expect with flat space. These wiggles here tell you that inflation happened, and the relative heights of these tell you how much dark and normal matter. So there's an incredible amount of information in this. Now, this is all WMAP. WMAP hasn't got great resolution, so all these results are from ground-based instruments, and the orange ones are from our own telescope up on Mount Tidy. The Americans have the very large array. We have the very small array. Okay. So that's done a great job. I should then say that there's a Planck spacecraft orbiting now. It has got 2 receiver systems that we've built at Jodrell Bank. They're working, all of them are working perfectly. In fact, it did actually show a little bit of data, and that corresponds to this bit. And basically, we see the same things, but with a factor of 2 or 3 greater resolution. We will know that plot precisely in about a year or so, maybe a year. I've seen some of the data. I'm not allowed to tell you what it's like, but it's very good. Okay. Now, so we can take the data from the CMB observations with the latest values of Hubble constant, about 74. We know what the universe is like now. It is lumpy and bumpy. It basically has voids, and the galaxies are around it. And all of that, we get a very consistent model of the universe. It's called the lambda CDM, lambda and cold dark matter, the dark matter being relatively massive particles. 4% normal matter, 23% dark, 73% dark energy. Age about that. The pressure produced by the dark energy is now making the expansion of the universe accelerate. We've talked about that. And this is quite recent, just a few months ago. This is what WMAP tells us very quickly. Helium was present before star formation. Inflation happened. There's no measurable deviation from that lambda CDM model. That looks okay. Space is flat to within 1%, and dark energy is within 14% of what you would expect if it's this lambda term in Einstein's equations. It all really fits rather well. And what's happened is that the age of the universe started off expanding quickly, gravity slowed it down, but then this dark energy is making the expansion increase at an ever faster rate. But one final problem. Sorry, I've got to be a couple of minutes over. Why is the universe fit for life? The fact that I'm talking to you. There are a number of parameters which have to be precisely right or very close to allow us to exist. Very quickly, n is 3 spatial dimensions. If n were 2, you could not have complex life. If n were 4, forces would fall off as the inverse cube. Atoms couldn't form. Another one is the ratio of the amount of mass that's converted to energy when you fuse hydrogen. If it were less than 0.006, it's actually 0.007, helium and the heavy elements wouldn't form. We couldn't be here. If it were greater than 0.008, there'd be no hydrogen left. We wouldn't have any water. So basically, that has to be quite right, along with a number of other things. 2 possibilities. One, a creator designed our single universe so it could support life. There's no way of showing that wasn't the case. Or, as people like Lord Rees would say, there are myriads, perhaps an infinity of universes, all with different properties, some of which, very similar to our own, would be suitable for life. One idea has come out of that inflation, Alan Guth's idea. They call it eternal inflation, in which once started, universes spawn indefinitely. It could be our universe is infinite in size, and beyond that, there are another infinite number of other universes. So perhaps Buzz Lightyear was right, not wrong. String theories you've heard of. They arose out of attempts to produce a theory of everything. There were 5 competing theories, 10 dimensions. 6 curled up to form little particles. How they vibrate, they're called strings. How they vibrate basically determines how they actually act. Ed Witten, you may have heard of, he showed that all these 5 theories were in fact just different manifestations of a higher theory he called M theory, and that has 11 dimensions. And there could be an infinite number of universes, all existing together, but without anyone knowing about them. And here's a very, very simple analogy for that. I've got oh, that's not going to work. This is meant to be good bread. I've got 3 slices of bread, and on them, can you imagine I put some little ants? Now, they can sort of walk around on each side, on one side, shall we say, and can you see they sort of think they were in a 2-dimensional universe? It's very good bread. They could live for quite a while, actually, on here. Now, that's all they know, and they would probably not know about the ants that were on this universe or that one. However, because we can think and visualize in 3 dimensions, not 2 spatial dimensions, can see they're just 3 2-dimensional universes in another higher dimension. It could well be that our universe is just such a thing, that there are myriads more universes, could be very close to us, but in another dimension. That's exactly what I've said here. One point about that is, does it sort of explain why gravity is very weak? They say it leaks into higher dimensions. Well, if you believe that, you'll believe anything, but that's probably true. Now, I want just, in fact, to quote myself, because I'm quite pleased about this. OK. Now, whenever I quote from people, I always put a picture, don't I? Have you noticed that? So I thought I'd better put a picture of me, but I scaled it so that my brain was about the right size relative to Ed Witten's. Anyway, now, if you read in the Gresham brochure, the final words of this talk, or about this talk, were that our universe could just be one small part of a multiverse that extends beyond our imagination. Now, you could say I was waxing a bit lyrical, because I quite like writing these 20-word thingies, but in fact there's more to it than that. What I was trying to imply, and I think it's a fair thing to say, was that the totality of the cosmos, which is everything, and the laws that govern it, might well be beyond the ability of our human minds to grasp. Does that sound at least a reasonable statement? That is what I really felt, and it's certainly true of mine. Now, that, to be honest, was my own thought. I'd never read or heard this said anywhere. I was very pleased when in the summer, notice his big picture again, Lord Rees, he in an interview with the Sunday Times, said the following. They wrote this: "Some of the greatest mysteries may never be resolved because they're beyond human comprehension, according to Lord Rees, present astronomer role," and they didn't put the bit about past progression of astronomy, which is unfortunate. Anyway, you get the idea, and he says that the inherent intellectual limitations for humanity mean that we may never resolve questions such as the existence of parallel universes and the like. So maybe my thought wasn't wrong. Now, he obviously never read what I'd written, because that wouldn't have been published till later on, but at least I have the same basic idea. So that's enough of that. So very quickly, our universe began as a Big Bang. This is a tree ring of the universe. The rings are far apart, but they're getting closer together. The expansion was being slowed by the gravity of the matter within the universe. And then about 4,000 million years ago, dark energy in effect overcame gravity, became the predominant force. And since then, can you see the rings getting further apart? The universe is expanding at an ever faster rate. It's interesting. We live at the only time-ish in the history of the universe when the magnitude of the dark energy and the magnitude of dark energy and dark matter are comparable, and also when we can observe the CMB. As the universe gets bigger, that gets fainter and fainter and fainter. And all of this has allowed us to learn everything I've told you in this lecture. We can also postulate of a future runaway expansion. In the past, you wouldn't have known about dark energy because there wasn't enough of it to observe. In the future, you'll know almost nothing because you won't see very much. Now is about the best time in the life of the universe in which to study it. We can still see the CMB, there's sufficient space to allow the dark energy to manifest itself. As the longest-lived stars come to the end of their lives, the evidence that lies at the heart of our current understanding will have disappeared. And as the clusters of galaxies move ever farther apart, carried by the expansion of space, there'll be less and less for astronomers to see. So it's a great time to be an astronomer. And a wonderful time to have been your Gresham Professor of Astronomy. Thank you very much. His life. Well, maybe he wasn't quite so wrong as he thought. So it certainly wasn't that particular universe. As you heard, I think, in my last lecture in detail, Edwin Hubble showed that the universe was expanding. Let's quickly look at how he did that. First of all, someone called Vesta Slipher, who doesn't really get the acknowledgement he really deserves, he measured the speeds of approach or recession of galaxies by measuring the blue, if they were coming towards us, or the red, if they were going away, shift in their spectra. You've all heard of the redshift. It turns out that 3 nearby galaxies were coming towards us, but the majority of them, the remainder, were receding from us. So he had measured the speeds of approach or recession of quite a number of galaxies. Now, at that time, there was a real debate about whether the so-called white nebulae, what we now call galaxies, were beyond or within our own Milky Way galaxy. Henrietta Leavitt gave the clue as to how to solve this problem. She had observed a type of very bright star, they're called Cepheid variables, after the star Delta Cepheus, discovered by John Goodricke, an Englishman. These stars increase in brightness quickly, fall away more gently, increase, fall away. So it's a very rhythmic oscillation of the star going in and out. These are very, very bright stars, some of the brightest stars we have, which means you can see them at great distances. That's good. She observed a whole range of them in what is called the Small Magellanic Cloud, which is down here. We're here. So they were always about the same distance. And she discovered that, in fact, the brighter ones were breathing more slowly, which is not really surprising. A bigger object is likely to be brighter. If you took a big bell and a little bell, the big bell would actually have a lower tone than the little bell. So the bigger stars are oscillating a little bit more slowly than the smaller stars. And those that oscillate with a period of about 30 days are typically about 10,000 times brighter than our sun. And obviously there's a range, but that's a particularly This title obviously comes from Buzz Lightyear, and he was slightly pompous, I think, or meant to be, and it was meant to be something that was obviously absurd. Well, I'm not so sure that it is absurd, and I hope that by the end of this lecture you might agree as well. Well, the subtitle for this lecture is The Origin and Evolution of the Universe in 60 Minutes, which is fairly tough. But one thing I would say, I have, over the past year or so, given lectures which fill out quite a few of the things that I shall cover, but not in the detail I have in the past. So you can learn more about Einstein with the lecture entitled Proving Einstein Right, more about the expansion of the universe and how Hubble found that out in Hubble's Heritage, about the Big Bang in the violent universe, about dark matter and dark energy in the invisible universe, and all about the cosmic micro background in the title The Afterglow of Creation. So if you can look back at those, you should be able to get some more details. I've got rather more words in the PowerPoint than I normally do. It actually makes a précis of the whole talk. But if you want to, I think the transcript was about 9,000 odd words, and I hope that will give you quite a good feeling of what's going on. Well, let's start. The universe as a whole must be beholden to gravity, because it's the only infinite range force that acts on neutral matter. Electrostatic forces tend to be short range because matter on the large scale is neutral. And of course, the first theory of gravity was Isaac Newton's. And a lot of people say, well, that's obviously wrong. In fact, it only does fail under extreme conditions. And the only case I think it fails in our solar system is to do with the precession of the major axis of the orbit of Mercury, which doesn't get quite right. That problem was eventually solved by, as you know, Albert Einstein. Way back in 1905, in what perhaps we could call his Annus Mirabilis, he produced two incredible papers. The first one was about the photoelectric effect, which in some sense is one of the foundations for quantum mechanics, which ironically Einstein did not like at all. And that was what he got his Nobel Prize for, nothing to do with relativity. And then his second paper, and actually it was a supplementary paper as well, was to do with what we call special relativity. And a fundamental part of special relativity is that light travels through space at a constant speed, you all know that. But the important thing is that no material thing, nor any information, however it's carried, can travel through space faster than the speed of light. I've highlighted the word through there, because it does not say you cannot travel faster than light. You can if you're being carried by the expansion of space. This happened very early on in the life of the universe, as we shall see. Think of a currant bun. You take some dough, you put some currants in it, you put it in the oven, gas mark 4 for 20 minutes or something. It comes out, hopefully a bit bigger, so those little currants will be further apart. They have not moved through the dough, they've been carried apart by the expansion of the dough. And that's the idea you have to think of. Well, in 1915, Einstein produced his theory of general relativity, which is essentially a theory of gravity. The theory is pretty complex. It's couched in tensor calculus, and even that wasn't in A-level mathematics when I did it. Almost exactly 50 years ago, I realised as I was coming down on the train this morning. Some nice things to say about it. There's a man that we should know about, but perhaps don't very much, called Chaim Weizmann. He, in fact, he was born in Belarus. He came to the UK. He became a lecturer in chemistry at Manchester University, my own university, in 1904. And in fact, he invented the way of producing chemicals using bacteria, in particularly acetone, and I think that made him very rich. But then he became a statesman, and he was the first president of Israel. So he was really quite a man. I think it was in 1922 he accompanied Einstein on a transatlantic voyage to New York. I should say this is the Aquitania and not the Titanic, which had gone down a bit before, which could well have been the boat that he was on. I did try and research this a little bit. Okay, now, anyway, at the end of that voyage, this is what Chaim Weizmann said. Einstein explained his theory to me every day. I don't need to say it. And on my arrival, I was fully convinced that he understood it. I think that's a lovely quotation. Oh, thanks for laughing. Anyway, now there's another nice story, which I think is true rather than apocryphal. This is the best picture I could find of Einstein with Arthur Eddington. And you may know, certainly if you go back to the Einstein lecture, that Eddington led the expeditions to try and prove that Einstein was right by looking for the deflection of stars close to the sun during a total eclipse. About 1918, a journalist came up to Arthur Eddington, Dr. Eddington, professor he might have been then, and said, "Sir, I believe you're one of only 3 people in the world, apart from Einstein, who understand his theory." And Eddington did not give a reply. After a bit, the journalist said, "Well, that's a perfectly good question, isn't it?" Eddington said, "Well, yes, I'm just trying to think who the other 2 are." So it's not the easiest of theories. Einstein's theory predicts that mass will distort space-time around it, and that gives the surrounding space what we call positive curvature, which means that anything travelling through that space goes in curved lines. To try and explain what it might be, let me try and give you an analogy, which I did give some years ago. You have to imagine a very odd planet, quite big. The lower half is normal, people live there. But everything above the equator is covered with ice, which is a particular sort of ice. It has no friction. The people on that planet are totally convinced that they're living on a flat surface. They're members of the Flat World Society, and they cannot be shaken from that conviction. I know it's silly, you have to accept that. 2 explorers decide they will try and investigate what happens above the equator. They get on 2 sledges 10 kilometers apart, and they basically fire them off simultaneously at the same speed, so they'll travel northwards over the surface of this ice. No friction, remember. Now, they will think that they would remain 10 kilometers apart. That's what would happen on a flat surface. They will be therefore slightly upset when they crash at the North Pole. Now, if they insist on believing that the surface of their planet is flat, the only way they could explain that is to suggest that there was a force that they might call gravity that's actually pulled them together. Do you see that? So gravity is a force that we make up to explain what happens in a curved space if we actually think it's not curved, because we can't appreciate the fact that space is curved. So maybe that helps a little bit. This is rather lovely. John Wheeler, great physicist of the last century. Matter tells space how to curve. Space tells matter how to move. Well, Einstein wanted to solve his equations for the universe that he thought existed at that time, a so-called static universe, unchanging inside. And this was the general consensus among astronomers in the early part of the last century. Now, there's a fundamental problem with this. Supposing there are just 2 things sitting there like that, and everything is just stationary, what will gravity do? It'll make the whole lot collapse down. So he had to invoke a constant called lambda, or sometimes the cosmological constant, which was in effect an anti-gravity term, which has the interesting effect that it's actually stronger the further things are apart, as opposed to gravity, which gets weaker. Now, if you have a force like that, you can see that if you have 2 objects that are just the right distance apart, the anti-gravity lambda force can exactly compensate for the gravity, and the thing remains steady. However, this is a totally unstable system. If they get very fractionally closer together, gravity wins, they'll fall together. If they get slightly further apart, anti-gravity, the lambda term wins, they will fly apart. So it was an unstable universe, and Einstein, when he realized this, called it the greatest blunder of